When you have the atomic orbitals, you have those wave functions. In the case of a hydrogen molecule like the one we have here, these atomic orbitals are going to overlap to form what we call molecular orbitals. Now, molecular orbitals happen simply because the end result is going to be what we call a bonding molecular orbital, or an orbital where you have constructive interference between the wave functions, and that allows for a lower total energy in that specific orbital. And electrons, as you recall from your general chemistry, they prefer lower energy states over higher energy states. Now, because of the principle of conservation of energy, if you create a molecular orbital that is lower in energy, the excess energy has to go somewhere, and that would be wherever you get your destructive interference between your wave functions. That will lead to what we call here an anti-bonding molecular orbital. It's important to remember that every time you combine atomic orbitals, the number of molecular orbitals that you get has to match the number of atomic orbitals that you used to combine to make these molecular orbitals. Now let's look at the molecule of methyl bromine and how the molecular orbitals are spread out throughout the entire molecule. There's a ton of different orbitals in this molecule. We're just going to focus on two of them, bonding, anti-bonding. And as you can see, there's some places where you can see some nodes, places where you're not going to find electrons. That's basically these empty spaces in the molecule. And then you have your regions where you have a high probability of finding electrons. Now, something important to take away from this image is that those molecular orbitals are spread out throughout the entire molecule. They're just not localized, rather that wave of probability spreads through the molecule. Each molecular orbital can hold 2 electrons, just like your atomic orbitals. In the ground state, electrons occupy lower energy molecular orbitals, while the higher energy ones remain unoccupied. These molecular orbitals are going to be the most important ones. The highest occupied molecular orbital, HOMO, and the lowest unoccupied molecular orbital, and LUMO. That HOMO-LUMO, you're going to see it throughout the entire course, because this is where most of the electron transfer in the chemical reactions that we study in the course, that's where they're going to take place. Now let's talk a little bit about hybrid atomic orbitals. When you look at simple molecules such as methane, for instance, you notice that the ground state electron configuration for that carbon atom can't really explain how carbon makes 4 bonds. These are 4 bonds, same length, same energy. But if you look at the orbitals associated with carbon, you have your 1s, your 2s, and your 2p. There is no way that the 2s and the 2p have exactly the same energy in the form that we have them here. Even if we consider an excited state, still doesn't explain how carbon makes 4 equivalent bonds, like the 4 bonds that we see in methane. However, the bond for methane is real, it exists, we've been able to measure it experimentally. So the idea is that carbon undergoes a hybridization. In other words, we mix that 2s and those 3 2p orbitals that all participate, and when we combine them, we form 4 equal atomic orbitals with a symmetrical geometry. The atomic orbitals must be equal in energy to form 4 equal energy symmetrical carbon-hydrogen bonds. That's kind of what we see here. These new hybrids are going to have a new name, so we combine 1s and 3p, so we make an sp3 orbital. Now all 4 of them have the same energy, they can be you have your maximum multiplicity, and it matches really well with the experimental data. The shape of an sp3 orbital results from having about a quarter s character, 3/4 p character, and it looks like this. It's actually much closer in appearance to a p orbital than an s, but that's because of that 25-75 split. To make methane, CH4, the 1s atomic orbital of 4 hydrogen atoms will overlap with the sp3 hybrid atomic orbitals of carbon. The resulting structure, the one you see here. You have 109.5 degree separation between your bonds. That's the maximum you're gonna get based on Vesper. We're gonna get into that in just a second. And that's pretty much it. Now, if you look at multiple bonds, double and triple, that's where things get a little bit more interesting. Let's look at ethylene or ethene first. In this case, we have 3 bonds, as you can see here, double bond, single bond, single bond, same thing on the right side. And each carbon in ethene must bond to 3 other atoms, so only 3 hybrid atomic orbitals are needed. So do I combine all 4? Not at all. I only combine as many as I need. In this case, I will take one of my s orbitals, my 2s, and 2 of my p orbitals, so lowest energy, and then whatever else I need. I combine, I used 1s, 2p, so I make an sp2 orbital. That's how I get that combination sp2 hybrid carbon that'll have 3 equal energy sp2 orbitals and 1 unhybridized p orbital. So this little red and blue here, that's p orbital that's not hybridized at all. It can still interact, it can still form bonds. That's actually how we get the second in that double bond, by having those p orbitals combined. The shape of an sp2 orbital results from having 33% s character and 67% p character. So it's going to look a little bit less than a p orbital. The sp2 atomic orbitals overlap to form a sigma bond. That's the one right here. I like to call it the internuclear bond because it literally crosses right between the 2 atoms. And then at right angles or perpendicular to it, these 2 will combine, these 2 will combine, and when they do, they form 1 pi bond. That's how you get your double bond. 1 sigma and then 1 pi. The pi bond is formed by side-by-side overlap of the p orbitals. The electron density of the pi bond is spread out above and below the plane of the molecule as shown below. So even though we actually have 2 areas, this one and this one, there is only 2 electrons, it's only 1 orbital. It's just that that cloud is spread out over those two areas. Pi bonds are weaker than sigma bonds. They're a little bit, they cover more volume, so they're easier to break. And as a result, they tend to be a lot weaker than your sigma bonds when you do a side-to-side comparison. Pi bond is described in a similar way according to molecular orbital. You still have your bonding, you still have your anti-bonding, and your electrons will be occupying the bonding before they go to the anti-bonding. Now, if you have more electrons, they can certainly occupy anti-bonding, but if they can avoid it, then they will. Let's look at a triple bond now. In the case of ethyne or acetylene, each carbon in ethyne must bond to 2 other atoms, so only 2 hybrid atomic orbitals are needed. So I grab my 2s orbital, one of my 2p orbitals, and because I only use 1s and 1p, it will be an sp orbital. That leaves me with 2 p orbitals that are unhybridized. I don't have to mess with them at all. The sp atomic orbitals overlap head-on to form sigma bond, just like for the double bond, right? Those sigma bonds form while the unhybridized p orbitals overlap side by side to form pi bonds. So what that means is that when I have a triple bond, I will have 1 sigma bond and 2 pi bonds. And this will be the resulting molecular electron clouds that we will see whenever we're looking at acetylene. You have combinations here for your pi bonds, and then this guy right here in gray would be your sigma bond. Now, just as a quick review, at this point, you should be able to answer these questions. Let's go over them together. Which should be stronger, a pi bond or a sigma bond? Sigma bond is always going to be stronger than a pi bond. Sigma bond is considered stronger as it requires almost twice the bond energy of a pi bond to break it. When we look at single, double, and triple, sp3 for single, sp2 for double, sp for triple, which one would be longer? The idea here is that your single bonds are going to be weaker and longest, followed by double bond, and then your shortest but strongest bond would be the triple bond. As you can see here, this is the actual experimental data. Your average bond length for your single, double, and triple, you see it goes from 154 to 120, and then in bond energy from 364 to 820, so more than double. Now let's talk a little bit about VSEPR. As you recall from your general chemistry, the VSEPR theory stands for valence shell electron pair repulsion, and it is a model that uses the repulsion that like charges have for one another to predict the geometry, both molecular and electronic, for any given molecule. This is actually pretty accurate for smaller molecules, and we like to use what we call the steric number in order to predict that the geometry that molecules tend to have experimentally. So we'll have three examples here. We have methane, we have ammonia, and we have water. We know the level of hybridization in each of these. This one has a steric number of 4 for sigma bonds or single hybridized bonds, so it's a number of 4. And, ammonia has 3 bonds, so it'll be 3 sigma bonds, and then water only has 2. Because of that, the hybridization of methane, sp3, sp2, and sp. And in this case, the steric number of all 3 of them will be 4, simply because we have to also account for the lone pairs of electrons. You can see we have a 4O, giving me a steric number of 4, 3, 1, and then 2 and 2. Because of that, when you look at the electronic geometry associated with all 3 of these species, they all have a tetrahedral electron group geometry. The bond angles are going to change a little bit, mostly because lone pairs tend to be a little bit stronger, they occupy more volume, they push a little bit more than your bonded pairs. So you will get a larger angle with methane, and then your lowest angle will be with water, and then ammonia somewhere in between. The molecular geometry is described for only the atoms bonded to the central atom. Electron group geometry includes lone pairs. It's important to make this distinction because in many cases, whether or not you have lone pairs will make a rather large difference in the geometry associated with any given molecule. Here we have a summary of some of the more common geometries that we're going to see with organic compounds. They go tetrahedral, trigonoplanar, bent, etc. I suggest that you sort of go over these, try to not necessarily memorize them, but try to familiarize yourself with them. Make sure that you kind of understand what these geometries are, because as the course progresses, you will notice that the structure and the shape and even the size of a molecule will determine the functions and the reactivity of any given system.